Okay, let's start. Good morning. So I graded the first midterms. The average is around 80, so I'm fairly happy about it. If you go to the assignment page on Canvas for midterm 1, you're going to see a key, so you can have a look at that and sort of compare what you did and how you could have done this last problem about the means and standard deviations and stuff. Okay, any questions about anything? We still have a couple things to discuss about metric spaces, and then we'll be on our way to differential calculus. So here's what we were discussing last week on Friday. I decided to call this the fundamental theorem of finite dimensional normed spaces. So this is sort of like the master theorem that I think we're going to keep using. It says the following: if I have a d-dimensional normed space W, and I have a linear transformation from RD to W, then all of the following are equivalent. A is invertible in the sense of linear transformations. A is a homeomorphism, so it's invertible in the sense of topology. A is a bi-uniform homeomorphism. That is to say, A is invertible in the sense of uniform spaces, and A is a bi-Lipschitz homeomorphism. So A is invertible in the world of metric spaces. And I told you that the last two I'm going to leave to you. And really, once you think about it, it all boils down to figuring out that so the moment A has a functional inverse, A inverse, which we know is it has to be linear, but it's also a bounded linear operator. That is to say, its operator norm, the operator norm of A inverse itself is a finite number. That's what it boils down to prove this. Before going into the proof of it, I want to discuss some of the consequences. And in a sense, while this is an important thing, for us, perhaps consequences are a lot more important. Let me see our consequences. Yeah. So to begin with, if I have a d-dimensional space, certainly RD is also d-dimensional, by the classification theorem for finite dimensional vector spaces, I know that there are linear isomorphisms from here to there, or vice versa. Namely, you would just choose a basis for W, and that would give you the so-called matrix representation, right? Or you can take any vector in W and think of it as a column matrix. That's an isomorphism. So such A's always exist by choosing the matrix representation. But because of these other parts, that the moment you have a matrix representation, that matrix representation is a homeomorphism, it is bi-uniform, it is bi-Lipschitz. This means that no matter how abstract your finite dimensional normed space is, for the purposes of continuity, uniform continuity, and boundedness, you can just pretend that it is RD. I'm not saying in terms of angles, though. Okay? This is not an inner product thing. This is a norm thing. Inner products is a different matter. And again, if your space is not finite dimensional, you don't get to use this. So in function spaces, this doesn't work. But in matrix spaces, it does. So for instance, and this is going to be a bunch of exercises, really. In any finite dimensional normed space, closed balls and spheres are compact, just like in the RD case. Because you see, closed balls and spheres, these are, so whether or not they are compact is a topological property. I'm saying topologically, any normed space, any finite dimensional normed space is the standard RD. So I can just duplicate all of the properties I have on RD to W. That W be a finite dimensional norm space, then any closed ball or sphere in W is compact. In W is compact. Bolzano-Weierstrass. Bolzano-Weierstrass is a topology thing. It has to hold. Any bounded sequence in W has a convergent subsequence. What else? I can say this more generally, this statement, namely that any subset of W is compact if and only if it is closed and bounded. So a subset S in W is compact if and only if it's closed and bounded. I can say more things. For instance, I can say any function defined on W that is uniformly continuous, or maybe I can say if a function defined on a compact subset of W, well, I guess that applies more generally, actually. I'm not going to say that. Let's see. Okay, there's one thing. Okay, I might mention it later. This is one set of exercises. Another set of exercises is perhaps more deconstructed. Namely, if I take any finite dimensional vector space, then in fact, any two norms on this finite dimensional vector space are proportional. If I have V, a finite dimensional vector space, then for any two norms, let's say 1 bars and 2 bars, let's say. There's a universal constant C, let's say, such that the first norm is C multiple of this, or upper bounded by a C multiple of this, and from below also. There's a C positive, such that for any V in V, the norm of V relative to the first norm is upper bounded by C times norm of V relative to the second norm, and from below, let's say 1 over C. Okay. So in the textbook, there's a statement that so we had the L1 norms, L2 norms, LP norms, and so on. In the book, there is, I think, an exercise that says that on RD, there is a, so let's say, I think L1, there is some constant C such that this happens, for instance. And then there's something from below also. This is an exercise in a textbook for finite dimensional. So for RD, they say, the fact that this is the case has nothing to do with LP norms. It has to do with the fact that this is finite dimensional. So up to some constants, any two norms are pretty much the same, okay? Insofar as you have finite dimensions. And the final thing, perhaps, is that if I have a sequence of matrices with the same dimensions, let's say that converges somewhere, right? Because I can think of a space of matrices as a norm space with the operator norm. Let A bullet be a sequence in the space of, let's say, m by n matrices. the standard way to think of this as a normed space is to use the operator norm. So if I'm saying a bullet converges to A infinity, to some other matrix, I need to say that in terms of the operator norms. This, when I write this convergence, this means in terms of the operator norms. But this is finite dimensional. And so really, this space of m by n matrices is nothing but r to the m times n. And so I can just use a Euclidean norm on this r to the m times n and just say, in order for this to happen, it is necessary and sufficient that each ijth entry of this sequence converges to the corresponding entry. Okay. And I can think of sort of open sets and stuff like that similarly, for instance, in the case of matrices. OK, there's more things that I want to say perhaps about this, but I might put them in the problem set for next week. One final thing I want to say is that another consequence, or yeah, it's a consequence we can say, is that in fact, this statement here, that let's say the unit closed ball is compact, is in fact equivalent to saying that W is finite dimensional. This is slightly advanced. We could prove it. We have all the tools actually to prove it, but it's not going to be fundamental for us. So let me just state it like this. Riesz theorem, let W be a normed space, then the unit closed ball centered at the origin in W is compact if and only if W is finite dimensional. If you take a more advanced class, probably you're going to see some version of this statement. Okay. Another thing too, obviously in analysis we use norms because somehow normed spaces are the best types of metric spaces, and when we want to take limits and stuff, we're going to use norms. But the point is that because of this bi-Lipschitz homeomorphism property, it turns out that in the case of finite dimensional norm spaces, it's not going to matter, qualitatively speaking, which norm you use to take limits. Insofar as that limit goes to 0, of course. Okay? So the value of the limit could change if the limit goes to some non-zero number or non-zero vector. But if it goes to 0, it doesn't matter relative to which norm you're taking the limits, okay? Any questions or comments about any of this?
And this can be extended to say, like, if you have a metric space with a sufficiently nice distance function and you're just measuring distance to 0 or something, like converging to 0 in that sense, like doesn't matter with your like distance function?
Well, I mean, eventually it still turns out to be the case that at least locally you want your space to have nice structures. So just like if I were to take a discrete metric, or if I were to take an arbitrary set and define a metric on it, I still want something about the local property. So I want some niceness about the open sets. I want it to be as close as possible to RD, really. This, in fact, leads to the notion of a manifold. Now, one of the things that we're doing in this class is really sort of preparing it to more advanced stuff. And I mentioned this to one of your colleagues earlier, I think 2 weeks ago. So in physics, there's a special relativity and general relativity, they say. I don't quite know, but it turns out that somehow with special relativity, you sort of focus on a piece that is flat. There's space-time, but it's not curved. When you switch over to general relativity, what ends up happening is that somehow there's an equation, there's a differential equation that tells you how the space should be curved. This is called the Einstein field equations, as far as I understand. And somehow special and general relativity, these two things are related to each other. And in a sense, it seems to me that special relativity is general relativity without sort of this global aspect. So you don't think about the global shape, you just focus on smaller patches of the whole space. And in this class too, that's what we're going to do really. We're going to do local theory. A lot of the theory that we're going to cover is going to be sort of local properties. When you sort of try to generalize it to nonlinear spaces, it becomes slightly more technical. And we already have plenty of things to worry about, I figured, so we're not going to spend that much time. But if you were to ever take a class in differential geometry, that's going to be the main topic. So you're going to learn how to think of spaces like the surface of a donut from an intrinsic point of view. We would like to imagine this to be embedded in three-dimensional space, but it turns out that this is not quite the right way to think about it, at least for many purposes. The point is that even if you have the surface of the donut, you can just focus on a small patch and pretend that it's a vector space. Okay? So for pretty much everything we're going to do for the rest of this class, we're just going to take an open set in some norm space, and we're just going to do calculus there. Okay. So in differential geometry, or if you take a topology and stuff, you're going to see more complicated objects like this. And then once you take differential geometry, you can go back to analysis and do what is called global analysis, which is sort of analysis done on these more complicated spaces, sort of like builds on top of each other. For us, the space is just going to be an open set in some norm space. It's going to be flat, much like special relativity. Okay, any other questions? Let's handle this. All I need to show is that A inverse has bounded operator norm. And in fact, let me write it here. Here's an exercise. Given a linear transformation, we associated 3 numbers to it. Operator norm, operator conorm, and their ratio, which is the bolicity. If A happens to be invertible as a linear transformation, operator norms and conorms of A turn out to be related to the operator norms and conorms of A inverse. Exists. then in fact, let's write it like this. Operator norm of A is the same thing as the operator norm of, the operator conorm of A inverse reciprocal, and likewise here. So they flip. And the same thing holds with the Lipschitz stuff as well. And so on. And in particular, for instance, the bolicity, the condition number of A is the same thing as the condition number of A inverse. These are nice exercises in inf and sup and all that stuff. So I'm just going to leave them to you. It's not that we're going to need it, but this sort of tells me something about what I should be doing in the proof. OK. Maybe I should mention this. Why should this be the case? Well, the operator norm is something related to rise over run. It's an upper bound on the rise over run. Well, an upper bound on the rise over run, when I take the reciprocal of it, becomes a lower bound on the run over rise. But the run over rise of an operator should be the same as rise over run of its inverse. That's sort of the idea. It's all about controlling rise over run, you see. Let's get rid of this part as well. OK, proof of theorem. Say it exists. I want to show that it's a bounded operator. That is to say, I want to show that its operator norm is finite. OK. Now, last week when I started this proof, what I said was I used this. I said, oh, it's nothing but the reciprocal of the conorm of the original operator. But we don't need to use that terminology, really. We can just take a vector in W and try to bound this. That's going to be sufficient. What you should keep in mind is that because of this reciprocal relationship, saying that the operator norm of A inverse is finite is the same thing as saying that the operator conorm of A is positive. So it doesn't shrink things to zero. That is the intuition. Okay. Let W be in W. So I'm trying to bound A inverse of W in norm. Okay. Trying to bound this guy. Let's see. Let's draw a picture. Here's RD. Here's this more complicated space, W. A goes from here to there. Somehow, I need to use something about A, right? I know that A is continuous by something we proved last week. Now, if I were to look at the unit sphere in RD, if I were to apply A to it, it's going to go to some other space. It's going to go to W, and it's going to become an ellipsoid, if you want, or it's going to be an ellipse. Now, A is invertible. That means that 0 vector in W is not in the image of the unit sphere under A. Okay? Because if A is invertible, AX equals 0 has a unique solution, which is x equals 0. So let me call this S. So this is the unit sphere in RD. And this ellipse is the image of the unit sphere under A. I'm saying that 0 is not in this image, in this ellipse. That is to say, this ellipse cannot be sort of degenerate, if you want. It cannot be passing through the origin. Well, why is that? If it did, well, I could just apply A inverse. Say 0 is here. Apply A inverse. The image of 0, I'm saying, has to land then to some other point on this unit sphere, which cannot happen, of course. Let's try that. Indeed. Then 0, which is A inverse applied to 0, would be in the unit sphere. Which is to say, its norm is 1. It's a very simple idea, but maybe the formalism makes it hard to grasp what is happening. Any questions about this? So you see, I'm leveraging the standard linear algebra stuff to do something with continuity. OK. What's more? By one of the exercises I gave you last week, we know that S is compact. It's a compact subset. Any sequence here has a convergent subsequence. It's a compact subset of RD. We also showed that any linear transformation that goes from RD to whatever has to be continuous. By the maximum principle, I know that this ellipse has to be compact also. By exercise, know that S is compact. By theorem that we proved, A has to be continuous. And by maximum principle, I know that the continuous image of any compact subset has to be compact. OK? Now let me look at the function that is the norm of W restricted to this subset. Consider let's say, phi restricted. So it's a function defined on this image, defined by take a w in this image and send it to its norm. Linear algebra is continuous, which means that this is a continuous function. So that this is a continuous function on a compact subset. By the maximum principle, it has to attain its minimum. Linear algebra is continuous, so phi is continuous. This is compact. By maximum principle, it has to attain its minimum. Okay? Okay? Now that minimum is not 0, because if it were, well, it would contradict this one. Which means that it's a finite number that is positive. Thus, there's an alpha strictly positive number such that for any w in this image, phi of w is bounded from below by alpha. So you see, I just used maximum principle a bunch of times and continuity of linear algebra stuff. OK. So let's open this up. What does it mean for w to be in the image? Then it must be the case that w is of the form a of v for some v, a tuple of numbers of norm 1. i.e., for any v in Rd, if the norm of v is 1, then a v, right, this is bounded from below by alpha. So you see, I'm just, this time, because I'm looking at A inverse, or rather the operator norm of A inverse, that's the same thing I told you. It's about controlling the operator conorm of A, which is about controlling how much A shrinks. So this is a lower bound as to how much A can shrink. That's the idea. But the only problem now is that this works only for V tuples of norm 1. I need to generalize it to arbitrary vectors. Well, in fact, I can just take it like so. It's going to be sufficient. So now, let w in w, I'm trying to bound the norm of A inverse applied to w. Certainly, if w is 0, there's nothing to do. So say w is not 0. Apply, so then this guy is not 0. I can normalize it. That's a unit vector. Okay. Then I can apply this to this, that vector. Right? So if I were to apply A to this vector, this is going to cancel out with this, and this is a scalar. I can take it out so that this becomes W in norm divided by this. And then I can take this to the other side and take this to the other side. So that A inverse is bounded indeed. You see, a lower bound as to how much A shrinks when you take the reciprocal becomes an upper bound as to how much A inverse expands. And W was arbitrary. I was able to bound the size of the output under A inverse by some multiple times the magnitude of the input for A inverse. That's what it means for A inverse to be a bounded operator. Comments, questions?
Can you explain how you go from the star line to the next line?
From here to there?
Yeah.
So I look at the star, and I'm saying, OK, so this vector is in the unit sphere. Well, I can choose that V then in the star to be this unit vector.
Okay.
And then I'm applying A to it. So maybe you have a question about this?
That's where they begin.
Yeah, yeah.
I think I see it. Yeah.
OK. So it's very important to look at the types of the objects that you're dealing with. Here, W is an abstract vector. A inverse is an operator. When you look at this, this is a tuple of numbers. Because A goes from RD to W, which means that A inverse goes from W to RD. This is an honest to heavens tuple of numbers. You can divide it by some number. When you take the norm of a vector, that's the number. So this is a scalar multiple of this particular tuple. And its norm is 1 by definition, because I just normalize it. So that I can take this particular vector and apply the star equation, or star inequality, like so. Comments, questions? This is not a super major important thing for us. So if you're somewhat confused, it's fine. Not a major deal. Not a big deal. You can just black box it, I think. You should know the fundamental theorem of finite dimensional norm spaces. That you should know and you should be able to apply. But the proof itself, maybe it's a little bit too advanced. Even though, as you see, we have used nothing but the things that we discussed so far. I used maximum principle at least 2 times. That tells you that it's an important thing. On a compact subset, I get to optimize things. Okay, that's an important aspect. I use the continuity of the norm. That's again important. Linear algebra is continuous. So that's that. OK. So we have about 10 minutes. This is all that we need, at least for now, about compactness. You see, this is really a consequence of the statement that the unit sphere in RD is compact. Let's think about the next 2 properties, namely connectedness, things related to intermediate value theorem. It turns out that intermediate value theorem is not that important in higher dimensions, at least as far as I'm concerned. And we also need to talk a little bit about completeness. I'm also going to not emphasize that much. As far as I see, completeness is not going to be a major issue for us. But if it turns out to be, then we'll go back. First, I want to give you this exercise. if I take a subset of real numbers, then the subset is an interval if and only if it is path connected, if and only if it is connected. What was path connected? It just means that given in 2 points in my set, I should be able to come up with a continuous path. I should be able to interpolate the 2 points. Okay? Maybe in a linear fashion, but maybe it's like a more complicated path. It doesn't matter. Connected is slightly more complicated in general. It says that you cannot disconnect it. Okay? Which means that if I were to take 2 open subsets that cover A, that are disjoint, then at least one of them has to be empty. So you don't get to separate. Again, these are not important properties as far as they're concerned. But if you were to take a more advanced class, let's say in topology, you're going to see sort of all the sort of different things about these different ideas. And the theorem about these is this. So this is the generalization of the intermediate value theorem. If I have a continuous function, so let x and y be metric, A be a subset, f be continuous on A, taking values in y, then if A is path connected, then so is f of A, the image set. And likewise, if A is connected, the image set is also connected. We might as well call this intermediate value theorem. I'm just going to leave it as a theorem. I'm not going to prove this. It's not a major proof. The proof is not complicated. All you should remember is that under continuous functions, all of these topological properties are preserved. If I take a compact subset, apply a continuous function, the image is going to be compact. If I take a path-connected subset, apply a continuous function, the image is going to be path-connected, and likewise for connected sets. Okay? I want to give you one important warning, though. It is not true that the image of an open subset under a continuous function is open. Okay? This is not continuity. It's a more complicated thing, which we'll encounter later. Warning. The image of an open under continuous function need not be open. And likewise, the image of a closed subset under a continuous function need not be closed. Open and closedness, they work backwards. All the other properties work forwards. This is an important thing. Okay. Now, the final theorem I want to mention is about completeness. Just like you learned in 30 to 10, When you have a sequence of functions, you can talk about pointwise convergence or uniform convergence. We had already discussed this uniform norm, or C0 norm, C0 metric, all that. Everything you learned basically applies there as well. I just want to state the following. And again, I'm not going to prove it. If later it turns out that we need to have a better understanding, we'll go back and prove it. Namely, theorem, let Y be a metric space. Then the following are equivalents. So we had completeness. This was about Cauchy sequences converging, really. It turns out that the completeness of Y has functional interpretations, namely, Y is complete if and only if for any set S, the collection of bounded functions from S to Y is complete with the C0 norm, C0 distance. If and only if for any metric space X, the collection of continuous and bounded functions from X to Y is complete. So if the output space is complete, then any function space pretty much is complete. This, of course, depends on the norm itself, but this is a good first approximation. Let me finish with this. Let's say cousin to this theorem. For normed spaces, let W be normed. Then W is complete. That is to say, W is a Banach space. If and only if for any normed space V, the space of bounded linear operators from V to W itself is a Banach space under operator norm. Okay. This is all I want to talk about continuity. Okay, this is the pre-calculus part of this class. Tomorrow we're going to start calculus. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to start calculus proper. Namely, we're going to spend basically 3 weeks on differential calculus, and then we're going to switch over to integral calculus. Turns out that in multivariable settings, differential calculus is perhaps more sophisticated. So when I taught 3210, I spent much less time on differential calculus, and I spent a lot of time on integral calculus, defining Riemann integrals and so on. That takes quite a bit of time. This time we're going to do it the other way around. And I'll say more when we get there as well, why I made that decision. I'm going to be taking attendance today. So there's an attendance sheet. OK, so are there any questions before we start? Of course, we start with the definition of differentiability. Definition. Now, this definition I'm going to give is the so to speak, local definition. Maybe later on, we're going to look at a more global way of thinking about derivatives. But somehow, the difference is going to be somewhat hard to sort of describe exactly what is the, what changes between local and global. So let's start like this. Let M in E and N in F be open subsets in normed spaces. So M is an open subset of the normed vector space E, and likewise N is an open subset of the normed vector space F. Okay. Now, what was the definition of an open subset? Well, open subsets were certain subsets of metric spaces. Let's remind ourselves. I'm not defining a metric space, but remember, any normed space is a metric space. Right? So the distance between any two points in E, and in particular in M, is nothing but the norm of their difference. And so, okay, what was an open subset? Open subset was a subset that was closed under perturbation. That is to say, M, for instance, is so that it's a subset such that if I were to take any point in M and just jiggle it around just a little bit, it's still everything that I get under these perturbations are still in M. That's the idea of open subset. Okay. And let me let F to be a function from M to N. Okay, this F is not the same thing as this F. So this means this is a collection of all functions from M to N. And let me let X to be a point in M. Okay. I'm going to say that F is differentiable at X if, well, basically I'm going to write down the definition that you learned in single variable calculus, and I'm just going to make adjustments so that everything works in the setting. If there is a bounded linear transformation from E to F such that, let's say there's a bounded linear transformation lambda, capital lambda, by the way, note that I am a lot slower today than usual. That should signify that this is important. So make note. There is a lambda, a linear transformation from E to F, such that well, I'm going to look at the rise over run, right? I'm going to look at the, so to speak, difference quotient. I think that's the name. So f of x plus h minus f of x plus lambda of h. Okay. Let me write this down, and then we're going to have a look at this formula. Like this, divided by h in E. Then I'm going to take the limit as h goes to 0. And I want this limit to be equal to 0. Okay, let's parse this. Okay, what is happening here? perhaps let's draw pictures. Here's E. It's a vector space. Here's F. I have a blob in E. It's an open subset, which I'm calling M. I have yet another blob here, which I'm calling N. Okay. Maybe it has multiple components, really. So in the textbook, under the section of connected subsets, they go on and on about connected components and stuff like that. I just skipped all that part because we're not going to need it as far as I'm concerned, as far as I can see. But there are things like that too. In any event, I have one blob here, and f is a function that goes from here to there. I have here an x. And of course, f of x has to be something, some point in this blob. F of x doesn't need to be somewhat in the center. Maybe it's somewhere here. Okay? Just drawing this like this for illustration purposes. Now, I don't know if for any h, x plus h is in M. But in this limit, I'm going to take h to be very small in magnitude. And in a second, I'm going to write down what this limit means also in terms of epsilons and deltas more explicitly. But the point is that if h in norm is sufficiently close to 0, by the openness property of M, I know that x plus h is going to be in M. Okay? This is a small perturbation of x, which means that f of x plus h too will be well defined, and it's going to be a point in N. In particular, it's going to be a point in F. Okay. So x plus h is somewhere here. So this is this part. And the way you should think about it is that basically you're trying to approximate this expression. You fixed x, and you're thinking of this as a function of h. You're trying to approximate this using a much simpler function of this form. Okay? So we saw how for linear transformations a bunch of things are equivalent, it being bounded, it being continuous, all that stuff. So that's what you're trying to use. First order approximation is what this is called. And again, if h is in E, and if lambda goes from E to F, then lambda h is going to be a vector in F. Okay? So this is a vector in F. This is a vector in F. I can add them up. This is yet another vector in F. I can subtract everything and then look at the norm of this whole expression. So the numerator becomes then a number. It's a scalar. H, again, the denominator, I'm going to divide by the norm of h. I cannot just divide by h because this doesn't make sense. You cannot divide by a vector in general. So I need to turn it into a number somehow. And so this is the most straightforward way to turn a vector into a number. Okay, and then once I look at this ratio of numbers, I'm just taking this limit as h goes to 0. Now what does this mean? This is not a number, so really I'm saying if h is a sufficiently small vector, I want this ratio to be a sufficiently small number also. In terms of epsilons and deltas, this means the following. i.e., for any epsilon, there is a delta such that for any h in E, if h in norm is bounded by delta, then that ratio is bounded by epsilon. And technically, in order for this to make sense, you need h to be a non-zero vector as well. Okay. Just like in the 3210 case. Okay. Any questions about this? Yes?
Is H and M?
Um,
I guess I'm confused why when we're looking also at the linear operator, it's going from E to F. Does it not need to be from M to N?
No. That is the one thing, okay? So let me put it this way. In a single variable case, this lambda in 3210, you learn that this lambda is a number. But we said that a number is the same thing as a linear transformation from reals to reals. Okay? If this just says that, of course, the norm in F is just the absolute value. The norm in E is just the absolute value again. So what you're saying is this. Just to emphasize that this is a number, I'm going to write lowercase lambda. Somehow lowercase lambda becomes a number in my head. Okay. Look at this expression. I want it to go to 0. Okay. Now, lambda is a number. And this is isomorphic to the space of all linear transformations from reals to reals. This is something that we discussed in week 1, actually, right? Now, that means that this derivative is a function not on M, not on the interval. Now, important thing here is that lambda, okay, is something associated to the point x. I'm not changing x. Okay, in a second we're going to vary x itself. But this is a function of h. I realize there's something very bizarre happening. And this is why I'm hoping to elevate maybe illuminate by switching over to the global terminology, let's say. But ultimately, somehow, you should think of it like this, okay? M and N, these are your configuration spaces. That is to say, these tell you where you are. Whereas h is a velocity. Okay? X is a position, h is a velocity here, really. What is bizarre here is that you get to add a position to a velocity. This is the bizarre thing, really. When you think about it, how do you get to add a position type object to a velocity type object? You get to do this because of the special or local nature of what we're doing. In general, you don't get to do this. Yes?
When you say it's position and velocity, you mean like, if you think about it as vectors, the position one is like the coordinates, and then the velocity one is like how much it goes in each direction?
Yes, ultimately. So think of it like this, okay? In principle, it is incidental that this set M is a subset in a vector space. M itself doesn't have any addition, really. From the perspective of M, you have no idea. You don't get to add every single thing. Okay, so this x plus h actually doesn't make sense for arbitrary h. It only makes sense for small h. Okay?
Yeah, we don't even say it's a vector space. So,
Yes.
addition doesn't even make sense.
Yes. I mean, in this case, it does. I get to bypass all that business by just taking M to be an open subset in E. But this is sort of me bypassing a bunch of things. And the reason why I'm calling this open set M is I want to think of it as a manifold. Open subsets turn out to be manifolds, but not vice versa in general. Okay, for us, at least for now, manifolds are just going to be open subsets. I just want you to think this is position information, but somehow this is velocity information. Yes?
Maybe you were about to do this, but can we do like an actual example with numbers?
Yes. Yeah, in an actual example, it actually doesn't make sense how you think of any of this, of course. But at least for now. So, yeah, OK. I'll pause the definitions. Here's a simple example. Example. Just going to take R2 to R2. Let's say f of x comma y is a nice polynomial function, x squared, y squared. Now, right from the get-go, you should look at this function and say, OK, the components are polynomials. If stuff I learned from wherever is correct, polynomials should be differentiable, whatever the notion of differentiability is. So this should be differentiable. OK? The problem is to figure out what is the derivative. What is a derivative? What is this lambda? So just going to look at this. Now, in the definition that we wrote, h was a vector. Now my vector is going to be h comma k. OK? So maybe I should write it. This is position. H comma k is velocity. OK. So basically what I'm going to try to do is I'm going to start with this expression and somehow, so far I wrote this part. I'm going to try to rewrite it in this form. There's going to be some residue or remainder. I'm going to hope that that remainder is small enough. Okay? This is how you take derivatives in higher dimensions. So what is this? Oh. OK. Opening this up, I have this. I just expanded the squares. Now, you see, I'm looking for a specific type of form. I'm going to write that expression as f of x comma y plus some other things. And you see, I already see f of x comma y here. I can split this vector. I have x squared, y squared here. And indeed, perhaps you can see that probably it's good to split this vector as this part first, so second order terms, and then first order terms, and then zeroth order terms. Okay, so I'm going to write it like this. Any questions so far? Again, why did I do this? Because I want to get something of this form, something of this form. The function itself plus a linear transformation. We still don't see perhaps a linear transformation, but let's keep going. At the very least, this is f of x comma y. Now, can I think of this as a linear function of the velocity vector? So in this case, the function is from R2 to R2. Lambda, which we're going to call the derivative of f at xy, should be then a linear transformation from R2 to R2, which means it should be a 2 by 2 matrix. So I need a 2 by 2 matrix here. And then this 2 by 2 matrix applied to this vector. What is this? So do I see, can I write this in this form?
It'd be like 2x and 2y on the diagonals and 0.
Okay. Now I get to do this, you see. You get to fix the position. I fixed x and y. Position is fixed. This is going to be my lambda. It's a linear transformation of the velocity. Okay. And I have some more things. Well, if h is small enough, h squared will be even smaller. And likewise, k squared will be smaller. So this is a higher order term that I can just ignore. In other words, if I were to take this, subtract this from it, divide everything by the norm of this vector, take it to 0, this is going to go to 0. This is a higher order term that I don't care about. And so you see, this is my lambda. It depends on x and y. It's, such is life. So let me summarize. Thus, at any point in R2, f is differentiable, and lambda is this. You're not happy about something.
The velocity thing is confusing me because if x and y are both positions, velocity should have some time derivative or something, should represent that, and I don't know what a time variable, I guess. I'm getting too into the physics.
Well, we'll get there later. Let me put it this way. Yeah. I guess just to give you some idea, what I can say is the following. This is my x comma y. And I want to think of h comma x as a velocity, that is to say, it's going to be a vector feathered to this point. Okay. And why do I think of this as a velocity? Really, when you think about it, you can say, oh, this is nothing but the velocity of a path that passes through this point that is tangent to this vector. You don't care what happens if it's far away, but eventually you want this to happen. You sort of get rid of the time derivative that way. You take a path, take the derivative of it, time derivative. There's a differential equations interpretation of all this as well, but we'll get there later. For now, at the very least, this computation should be clear. Any questions about this example?
Why could you just ignore the h squared and k squared?
Because it's a higher order term.
Right.
Okay. So I did all this, okay?
Yeah, that makes sense.
So let me rewrite everything in this term and take limit to 0. Insofar as the limit of this minus this divided by the norm of hk goes to 0, that is the lambda in the definition. So what do I need to do? I need to then look at this. This is my velocity vector. I'm taking its norm. I'm going to take it to 0. Which norm? We discussed this yesterday. It doesn't matter. If you want, you can use the Euclidean norm. So I'm going to write it like this. Okay. The question is this limit 0? Well, what is this difference? Oh, sorry. What is this difference? It is nothing but the norm of this guy. Right? Because this is nothing but this minus this part. Well, I guess I don't need this much. H squared, comma k squared, and norm. Now you can, if you want, open this up. You can say, okay, numerators are higher order. These are going to decay faster than this does. This has to go to 0. Okay? If you don't believe that, you open everything up. So let's use the standard Euclidean norm. What is this? It says h to the 4 plus k to the 4 in square root, and then the denominator is h squared plus k squared in square root. So this is ultimately h to the 4 plus k to the 4 divided by h squared plus k squared, everything in square root. Okay. Do I need to convince you that this limit is 0 at this point? The numerator is a higher order thing. It has to go to 0. Yes? And so if you want h and k, you can imagine h and k to be less than 1. So this is the linear thing. This is squared. This is cubed. This is the fourth order, whatever. If the numerator decays faster, it has to go to 0. Yes? Okay. Does this make sense? Any other questions about this example? Yes.
On the input there, that kind of makes more sense to like see it as the point and then the radius around it.
Yes.
So what would the output look like? It'd be like x squared, y squared, and then what would the radius line thing be? Would it be the 2x, 2y?
Well, that is where things get complicated because this is the output, right? Even if I were to say this is a unit vector, this is not going to sort of chase a circle itself. Okay? I mean, you can, if you want, you can plot this. Yeah. On a graphing calculator, fix 1 and 2, let's say here, as x and y. And then as functions of h and k, you can plot what f looks like. But its graph is going to be in a 4-dimensional space. It's not going to say much, probably. Okay. This is one of the complications in higher dimensions. It's like, even if I were to just stick the finite dimensions, OK, how do you even imagine a function from R2 to R2 even, right? OK, so maybe with R2 to R2, you can do things with like a heat map, or maybe you can use colors and stuff like that. But OK, then you switch over to machine learning, and then you have 10,000 parameters. Just like good luck trying to visualize it. I mean, people do it, of course, but. Any other questions about this? Now, the one thing that is perhaps different is that when you're doing single variable, typically what you do is you don't look at this rise over run like this. Okay? I mean, if you took 30 to 10, you're familiar with this idea, of course. But typically what you do is you get rid of this part, and you take the limit of this. And whatever that limit is your derivative. So maybe I should say something about this. So in 1D, right, so this is what you do. You take h to 0, and you call this the derivative. This is a standard way to do this. But when you think about it, this converging to this is the same thing as their difference converging to 0. Right? So I can just instead ask for this. But then so this converging to 0 is the same thing as, well, I can just take this to the numerator if I were to multiply this by h. And of course, the absolute value of the ratio is the same thing as the ratio of the absolute values. From a practical point of view, though, how you compute the derivative in higher dimensions work kind of differently. You don't get to just look at, OK, this thing, and I'm going to take the limit. If it converges, that's the limit. Instead, you want to look at this from this perspective. You want to start with this, and somehow you want to sort of split this function as the 0th order term and then the 1st order term and so on. So somehow in higher dimensions, it's better to sort of approach derivatives from the Taylor approximation perspective. Okay. Any other questions? Now, specifically, maybe I should mention this as well. So for instance, if I were to say x is 1, y is 2, then lambda becomes a numerical matrix, of course. It becomes a specific thing. If I were to look at the derivative, the lambda at a different point, OK, the derivative will change. OK? So here are some exercises. First of all, as this example perhaps gives some evidence of, if such a lambda exists, it has to be unique. And if such a lambda exists. That is to say, if f is differentiable at x, it has to be also continuous at x. Exercises. Nope. At x. Then the lambda in the definition is unique. And this unique bounded operator is denoted by, well, f prime of x. OK? And f prime of x. OK? Sometimes you would also see df of x. If f prime of x exists, that is to say, if f is differentiable at x, it has to be continuous at x, just like in the single variable case. And I can start with a linear transformation to begin with. So assume that f is a linear transformation. Then it is a bounded operator if and only if it is differentiable at any point, if and only if it is differentiable everywhere. And in that case, the derivative, of course, is the transformation itself. If, let's write it like this, from e to f, then L is bounded if and only if L is differentiable at some point, if and only if it is differentiable everywhere. And in this case, of course, the derivative of L at any point is itself. L prime of x equals L. Okay. And in fact, it goes backwards as well. If you have a function that is equal to itself at any point, that function has to be a linear, bounded linear operator. But let's not get there. Let's not go there. This is a very nice exercise. Okay? Which justifies this idea that, oh, you know, for linear transformations, boundedness, continuity, uniform continuity, Lipschitzness, and now differentiability too, they're all the same thing. Doesn't matter. OK. Now, I guess let's continue. I'm going to say that a function f from m to n, open subsets in normed spaces, is differentiable if it is differentiable everywhere. If it is differentiable at x for any x in M, well, in this case, then, I have f prime itself as a function of x. You see, so far, we had f prime of x, but this wasn't yet a function. But if f is differentiable at any point x, then f prime itself becomes a function. In this case, the derivative of f is, maybe I should write it bigger, continuing here. Oh, bounded linear from E to F. Now, in our example, for instance, so m were equal to E, which was equal to R2, n was equal to F, which is equal to R2. My F from m to n was x squared y squared. We computed f prime. Okay. Okay. Goes from M. The derivative was a 2 by 2 matrix. Which is given like this. This is what we computed. In finite dimensions, any linear transformation is bounded. In arbitrary norm spaces, I do have to require that the derivative is a bounded linear operator. Okay? Otherwise, things somewhat break down. Any questions about this? Okay? Well, M is an open subset in a norm space. In particular, it's a metric space. Space of bounded linear operators between norm spaces is a norm space under the operator norm. In particular, it's a metric space. If I have a function between metric spaces, I can ask whether or not it is continuous. That is to say, I can ask if f prime, this function, is continuous. If it is, I'm going to call f continuously differentiable and write it, I'm going to say f is in C1. And it's a continuous function from here to there. I'm going to call f continuously differentiable, and I'm going to write f is in C1, once differentiable, with a continuous derivative. Continuously differentiable. And write in particular, of course, in our example here, this is a continuously parameterized matrix, right? Because convergence in this space, even though in principle it's in terms of operator norms. Yesterday we discussed in finite dimensions, I don't care what the norm is. I can use whatever norm for convergence purposes. Certainly, then this has to be a continuous function. That's a good exercise for you to verify. That is to say, this function is continuously differentiable. Now you see, this is a complication in a sense. In single variable, we're used to having a function from one space to the other one, and an f'2 is from the same space to the same output space. In higher dimensions, when you differentiate objects, the input space stays the same. The output space gets more complicated. When you take the second derivative, which we're going to do later, the output space is going to become even more complicated. Okay? This is one of the main sort of differences between single variable and multivariable. Any final comments about or questions about this? Make sure that you understand this example really well. Okay? Look at other polynomials perhaps. Look at mixed polynomials. Okay, I think it's a good place to stop. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to keep working on the definition of differentiability. I would like to introduce things like the chain rule. Of course, chain rule should apply. That is to say, somehow we should be able to decompose the derivative of the composition of two functions in terms of the derivatives of the parts. And then maybe we'll look at more examples, and then perhaps define directional derivatives, all that stuff, give you more examples. But before that, I want to introduce slightly different ways of writing this condition of differentiability. One of them is going to involve what is called the asymptotic notation. It's going to come in handy, especially once we start talking about Taylor approximation also. So the standing assumption is this, okay? I have E and F, two normed spaces. So these are vector spaces. And on E, I have some notion of magnitude. On F, I have some notion of magnitude. These could be tuples of numbers, spaces of matrices, spaces of operators, some function space. I don't care, okay? Axiomatically, everything we're going to look into is going to apply. And M and N are two open subsets, M in E and N in F. So open meant that if I were to take any point in M, in principle, M and N could be empty, of course, but then it's kind of boring. So we're assuming really M and N are non-empty also. But in any event, if I were to take any point in M and move it just a little bit, perturb it, that is to say, it's still inside M, okay? You don't get to escape M under perturbations. And likewise in N. And here's a recap. If I have a function, f from M to N, okay? And if I take a point x in M, okay? I'm going to call f differentiable at x if a certain limit is 0, right? That's how I defined it yesterday. Let's write it again. Limit as h goes to 0. I want this limit to be equal to 0, where now, after this exercise I gave you yesterday, this f prime of x is a unique bounded operator. If it exists, it has to be unique, okay? For some unique bounded operator f prime of x. Let's write it like this. Okay. Now, differentiability, when we're talking about differentiability at a point, note that I so far fixed x, and f prime of x is a fixed operator. That is a derivative at a point. When I'm thinking of this as an operator, the input is h. Okay, f prime of x, this is one operator. It is applied to this vector. Okay, goes from E to F. This is one of the complications when you switch over from single variable to multivariable. Single variable calculus, this f prime of x is, you can think of it as a number. In multivariable, you don't get to do this. It is a transformation. At best, you get to think of it as a matrix. But even that is like, even in finite dimensions, that turns out to be somewhat dubious at some point. I hope at some point we're going to see some examples of that also. OK. How else can I write this? Well, one thing I can do is, the denominator here is a number. And in the numerator, too, I'm taking the norm of a bunch of vectors, ultimately. So I can take this number and sort of distribute as a scalar. So that maybe I can get something closer to what we know from single variable. I want to get something like this. This goes to f prime of x. Trying to get something like this, okay? But you're going to see how this doesn't quite work in this situation. So if I were to take this as a scalar, so that is to say, it is 1 over this number, scaled by the norm of this vector, I get to take the scalar and distribute. And write this whole thing like so. Like this. Okay, so this is this part. And then I have a minus. And you see this is where things go haywire a little bit. Because in the numerator here, this is a vector. If you take a vector, multiply it by its norm, it's still a vector. So you don't get to go over here. The numerator, so the h in the numerator and the h in the denominator, they are sort of a different type if you want. Remember, I get to do this because this is a linear transformation. I can take the scalar inside. Okay. No, but you see, this is as far as you can go. From here, I don't get to say, oh, if this is the case, then I can take this to the other side. Because this too depends on h. Okay, that's the problem. You don't get to write derivatives in higher dimensions like so. You have to use that sort of more intrinsic definition. You have to set up this limit, and you have to say, OK, can I found a linear operator such that this limit is 0? OK. Now, another thing, though, you can do is this. Instead of saying, OK, I'm looking at f at x plus h, well, instead of x plus h, you might write maybe y, and then you can take y to x. Right? So instead of in single variable calculus, instead of taking this limit as h goes to 0, you can also look at the limit of f of y minus f of x divided by y minus x. And then you could take y to x. It's the same thing, of course. These two are the same things. You can do this here too. And depending on the situation, you may want to do that. So let me write it like that as well. And so what is the change of coordinates, so to speak, to go from here to there? Well, you set up y equals x plus h, and then h becomes y minus x. That's the change of variables. And certainly, if y equals x plus h goes to 0 if and only if y goes to x. So h is y minus x, and h goes to 0 if and only if y goes to x. This is like a simple change of variable. Depending on the situation, it might be more useful to think of differentiation this way. And in higher dimensions too, you get to do this. So I can write limit as y goes to x of f of y minus f of x plus f prime of x. Instead of h, I need to put y minus x here. Okay, can do this as well. And then in the denominator, instead of h, I'm going to see y minus x in norm. I don't quite like this formalism, but you'll see this in the literature. And sometimes it is useful, so I just wanted to mention it. Any questions about any of this? Okay. So now I'm going to introduce this little o notation. If you've taken 3210 from me, you know what this is about. You spent plenty of time. There were problems in the problem set and so on, but some of you might be not familiar with this idea. And so instead of writing the limit of this ratio, I'm just going to write the numerator equals little o of the denominator. This is the numerator. I'm dropping the norm as well. I just don't want to keep writing norms and stuff like that. I'm sort of trying to simplify the notation in a sense. I'm just going to write this is this. And if I want to be more specific, I would write this. And you would read it like so. F of x plus h minus this expression is equal to little o of h. What this means is that whatever this expression is, it decays faster than this does as h goes to 0. That is literally the same thing as saying that that limit is 0. Okay? So you would read this right-hand side as little o of h. Or h in norm if you want. Little o of h. And then you get to do things like this as well. If you have an expression like this, you would take this on one side and send this to the other side, and you get to add this little o to this part. I'm going to stop writing the subscript, and this h goes to 0 as well. It's clear in this context, little o is supposed to be toward 0. And so, you see, this is somewhat more convenient once you get used to it. You just say that f of x plus h is f of x plus f prime of x times h up to higher order terms. Okay? You could say this as well. in this situation, of course, so this term is the 0th order term. This is the 1st order term. You're looking at multiples of h here. Okay? And then there's some higher order terms, higher order in h. Now you should think about what does it even mean to look at h squared, h cubed, and so on. We're going to make sense of all that. But certainly, in 1 dimensions, this should make sense. This should be familiar to you in that this is really saying that this is the 1st order Taylor polynomial approximating this function. Okay. Now, this is also a very good time for you to go back to your 3210 notes and review Taylor approximation, Taylor series, all that stuff. We're not going to take, we're not going to turn this into a series, at least for now. In principle, you do that too, though. But you should remember that for Taylor approximation, however many derivatives you have available for f, you get to basically pretend that f is nothing but a polynomial in h. Okay, this is an important theorem that we're going to discuss later, probably this next week. But this is really the core. Okay. Any questions about any of this? Now, I'm not going to formally define this little o. Just know that writing this or this or this they're all the same thing as writing this. In 3210, I defined this formally, spent some time, gave examples. There's also big O, somewhat slightly, it's a different sort of thing, similar to little o, but it's slightly different. So I discussed all of these, and you can have a look at the lecture videos from 3210 if you want to get accustomed to that. For us, all that matters is that this is nothing but a convenient way of writing this. Okay? And I personally really like, it's very convenient. Okay. Questions? Now let's go back to this example that we were discussing yesterday, because one of your colleagues, you asked about how things look a little bit, and then I thought about it. Because in that example, we had a function f from R2 to R2. How do you even imagine differentiability, things like this? And so this is what I came up with, okay? This is the example that we discussed yesterday. F, in this case, is defined on R2. So M equals E equals R2, and so are N and F. Okay, takes x and y, sends it to x squared, y squared. We computed the derivative. So if I were to fix x and y, f prime of x and y is supposed to be a linear transformation, right? So this, okay, is supposed to be a linear transformation from the first norm space to the second norm space, in this case R2 to R2. But at this point, I think it's OK to just identify linear transformations, or rather the space of linear transformations from R2 to R2, the space of 2 by 2 matrices. So we identified this to be this. So diagonal matrix with 2x in the first entry and then 2y in the second entry. Okay, and of course, when I write it like this, I mean this is a transformation so that you feed the input vector here. In principle, you could input that vector here too as a row vector, right? That's again a 2 by 2. That's again a linear transformation. But when we write it like this, I really mean this f prime of xy takes hk and sends it to 2xh 2yk. Okay? When I write it like this, I mean this. In this case, it doesn't matter because it is diagonal. In general, one has to be careful. Okay, so let's fix a specific point. Let's say x is 1, y is 2. So, yeah. So, at this specific point, f is 1, 4, right? F of xy is 1, 4. So fix. And f prime is, what is it? 2, 4. Okay? Any questions about this? Once I computed these, I just plug these numbers in. Assuming these formulas are correct, okay? Assuming this formula is correct. Are we happy with this and this? Okay. So let's try to get the sense of this derivative, or how one can use this. And basically, I'm going to use this idea. The idea is this. At this particular point, say you computed your function, and somehow you also know the derivative at this point. Now, at the nearby point to 1, 2, you want to compute the value of the function. But you say to yourself, OK, this function is complicated. I just don't want to be computing explicitly. So I'm just going to bite the bullet and say, OK, maybe I don't want to compute on the nose. I allow some error. OK? If you allow yourself some approximation, some error, you get to use the derivative to compute the value of the function at the nearby point. So, for instance, let's look at f of 2, 2. In this case, of course, the function is not that complicated, so it's straightforward to compute things. But you can imagine how things get very complicated very fast. So let's look at f of 2, 2. So this is, of course, 4, 4. This is the true value, true output. Okay. But I want to say something like this. So I want to say, how should I write it? Yeah. F of 2, 2 is the same thing as f of 1, 2 plus 1, 0. Okay. This is equal to f of 1, 2. So you see, now I'm trying to use this. My h is 1, 0. My x here is 1, 2. H is 1, 0. H is not small, OK? So there's going to be a large error. But let's still compute. This plus the derivative at 1, 2 applied to this 1, 0. Plus higher order terms. Okay. this higher order term is going to come out as a number as well, because everything is numerical here. Okay. So what is this? F of 1, 2 is 1, 4. What is this? This is the diagonal matrix 2, 0, 0, 4. And I need to apply it to this vector plus higher order terms. What is this? This is 2, 0, 1, 4 plus 2, 0. Plus higher order terms. Okay, so what is this ultimately? 3, 4 plus higher order terms. So this is the approximate output. You get to say then 3, 4 is an approximation to the true output. What is the error? The error is exactly, what is the magnitude of the error? It's exactly 1. You see it's at the same size as the size of h. So this is the approximate output. So this. So let's plot these. Diagonal, this, okay, then like so. Okay. Okay. What are our data points? Initially, this is 1, 2. And I know we're taking these as things that we know for now. We have these. Okay, we have these. In particular, I know where f takes this point. Takes it to 1, 4. This gets sent to this point. I don't get to see just now what this f prime does here, f prime of 1, 2. But OK. Now I ask, how about this point? Maybe I should use a different symbol. Triangle. Even though in this situation we could compute, you should think, in general, you don't have access to this. Hard to compute, OK? This is hard to compute. So in this example, we could actually compute it, but you should think of it as, oh, this is something you don't have access to, really. So 2, 2 now goes to 4, 4. But once you have f, the value f, and the value of f prime at 1, 2, you have this approximate output. Okay? The approximate output, in this case, is 3, 4. Okay? This is the true one. This is the approximate one. Any questions so far? Yes?
So you would use the approximation if you only have the derivative of it at one point? As
Yes.
Okay.
Yes.
Then how would you have the 2x, 2y thing
Well, if I was given a different point, the derivative would be a different matrix.
Oh, okay.
Everything depends on the point. Okay, so you can stop here and you can say, for my purposes, this error of 1 unit drift is fine for me. But ultimately, the point of writing here higher order terms is that the smaller this vector is, the better this approximation should be. Okay? The distance between these two should get closer and closer. So the approximation should match as close as possible to the true value. And the smaller your h vector is, the smaller, the better the approximation should be. Okay? So now let's take, instead of 1 over n. I'm going to take n to infinity, of course. And so you say, I know the value of the function at this point, and I knew the derivative, and I want to guess what is the value at this point. But then you say, OK, so if I were to try to approximate the value of this using the first order Taylor approximation, right, the error is like this. For now, let's say that we don't get to think about higher order Taylor approximations. We're going to do that later. But let's just try to say, then I'll just take the triangle to be closer and closer to the value, to the point where I know the actual values. And so f of, let's say, 1 plus 1 over n, 2. Again, in this case, we can compute this. So this is 1 plus 1 over n squared, and then 4. And this is 1 plus 2 over n plus 1 over n squared, comma 4. This is the actual value. But now let's try to use this approximation. I split this, again, like this. Okay. This, I say, is equal to f of 1, 2 plus f prime of 1, 2 applied to this vector plus higher order terms. And then what is this? This is 1, 4 plus 2 over n, comma 0, right? Because I'm applying 2, 0, 0, 4 to this vector. Plus higher order terms. Okay. So that ultimately I get this. Okay. So what is happening here? As I'm taking n larger and larger, this triangle gets closer and closer horizontally to the blue point. And as you see, both of these too get closer and closer. And what is the difference between the true value and the approximation? Well, it's this higher order term. As n goes to infinity, 1 over n goes to 0. 1 over n squared goes even faster to 0. Okay? This is all there is to it. Any questions about this example? This is a fundamental example. It's very simple, but I'm telling you, it doesn't matter how abstract things get. Same considerations apply. It's nice. Let's talk about chain rule. Oh, before I continue, I should say one more thing. Some of you after last class made the following observation. They said, if this is my function, well, I get all this, mumbo jumbo that you're doing, but really, this is this matrix. This is the matrix of partials of this. Okay. So they said, let me write the two components of f as f1 and f2. So f1 of xy is x squared, and f2 of xy is y squared. And then they say, OK, so I can just take the partials of these. First derivative should be about first partial, so I'm just going to look at the first partials. X partial of f1 is what? 2x. What is the y partial? OK. And likewise here, x partial of this is 0, and the y partial is 2y. So xy to y, so that really this derivative matrix is nothing but the derivative of the partials. How many of you have seen something like this before? Some people don't see it, they don't cover it. In differential equations, you might have seen this idea of a linearization of a differential equation. It's the same idea. This is true, of course. It does work, and it's no coincidence that it works in this situation. But the point is that, first of all, in this nice example, I could safely identify operators from R2 to R2 as 2 by 2 matrices. You can imagine it gets more complicated in general. Okay, so for instance, if I had functions defined on matrices, so for instance, if I were to ask you the derivative of the determinant, you would have a lot more trouble. You can do it still, but it's gonna be more painful. That's the first reason. Second reason is that it turns out that even though all of these partials exist, it might be the case that the function is not differentiable. So it might be the case that paradoxically, you might have all the entries of this supposed matrix without them compiling into a matrix that fits into the limit. Okay? And so that's why I'm taking the other way around approach, where we're holistic. I'm just taking the definition of differentiability from single variable, and I'm just saying I'm just going to generalize it to higher dimensions. I'm just going to take the limit, interpret it in higher dimensions. We're going to see when you get to compute derivatives this way. But for now, let's just leave it at this, okay? It's not a coincidence that you get to do this here, but more generally it becomes more cumbersome. And you can also see how much more I had to write, right? And this is a polynomial. Imagine I gave you more complicated functions. It's going to be a painful thing to compute these things. But then again, probably it's going to be hard to compute this as well, in any event. So we'll get there later. This is one of the reasons why I emphasize linear algebra this much. So when I think about it, a matrix is not, so for me, knowing a matrix is not knowing its components, right? Matrix is sort of like a holistic object. It's a global object. Then if need be, I can index into the specific entries I need, depending on the case, if they're available. OK, so chain rule. I'm going to need one more norm space and an open subset in it. So let's say M and P in G. Be an open in a normed. And let's let G be another function. And P, this is F, this is G, this is the composition. Let's say that both F and G are differentiable. Let's say F is differentiable at x, G is differentiable at f of x. Or maybe, yeah, OK, let's write it like this. If F is differentiable and G is differentiable, then so is G composed with F. And of course, the derivative of G composed with F at any point x satisfies the expected rule. And for any x in M, G composed with F prime at x is G composed with, or G prime at f of x times f prime of x. In this case, of course, these are supposed to be operators. And when I write it like this, I mean operator composition, if you want. It's a linear operator, I know what it means to compose operators. OK, so you can prove this using epsilons and deltas, but I'm going to use this little o notation. You're going to see how things get very convenient. So get this expression. OK. OK. Now, I know that f is differentiable at x. So I can write this using this little o notation. This is the benefit of little o. You get to apply functions to it. If you have this ratio and the limit of the ratio, it becomes more complicated, as you see. It's somehow this formalism is equivalent to the other one. But then now, to this expression, I can apply the fact that g is differentiable at f of x. And so imagine this, so to speak, h for g. This is this plus this times this expression plus O of the same thing okay. This is why little o some people don't like. Gives you expressions like this, but when you think about the definition, it's going to work out fine. First of all, I get to distribute this. And certainly this is the 0th order term plus g prime at f of x times f prime of x at x plus I have some other things. We're almost done. In fact, we are done by the following observation. This little o of h represents something that decays faster than h does as h goes to 0. Well, certainly a constant multiple of a 2 is going to have that property. Because of this, you get to have little o of h absorb this expression. Likewise, this is supposed to be something that decays faster than this does. But this decays faster than h, which means, or at least as fast as h, which means that this too is little o of h, which means that all this junk is just higher order terms. Okay. But then I get to approximate then, g composite f at x plus h as the function at x plus a bounded operator applied to h up to higher order terms. Right? So this is a bounded operator, this is a bounded operator. We showed in first midterm the composition of two bounded operators is bounded, so this too is a bounded operator. And this has to be the derivative of this then, by definition. That's the end. It takes a while to come to terms with this equation, this equality. Some people really dislike it. If you don't believe me, you can just use the epsilon delta proof that you learned for the single variable chain rule. It's going to pretty much apply here as well. In fact, I'm going to leave that to you. Exercise, prove using epsilon delta. It's going to take longer, of course, but works the same. Okay. So chain rule, you have chain rule. And based on our notation, it works pretty much the same way as you know from single variable. Okay, good place to stop. I'll see you on Friday. Okay, let's start. Good morning. So today, I'd like to introduce some more definitions around this first derivative. Specifically, I would like to define directional derivatives and partial derivatives, at least one version of them. And then, before continuing any further, I want to do a couple more examples that are slightly more sophisticated than the x squared, y squared example we discussed before. Before I start, are there any questions? Okay, so let me remind you as usual, we have the standing assumption of having two norm spaces, E and F, two vector spaces, maybe finite dimensional, maybe infinite dimensional, maybe E and F. These are spaces of tuples of numbers. Maybe they are spaces of matrices, spaces of functions, whatever. I don't care. And I have two sets, M and N, open subsets. These are sets that are closed under perturbation. If a point is in M, for instance, any nearby point too is in M. This is, so open subsets for us are going to be, at least for now, the proper sort of spaces between which we think about differentiability. If I have a function f from M to N, I'm going to call it C1. I had defined this before, but I'm reiterating. That is to say, continuously differentiable. If f prime exists as a function, that is to say, for each point x in M, there is a bounded linear operator from E to F, denoted by f prime of x. And furthermore, this function that takes a point x to the operator does it in a continuous fashion. And that is this f prime. So f prime exists and is continuous. Okay? What does it mean for f prime to be continuous? Well, M is an open subset in a norm space, which in turn is a metric space. Okay, so I have a metric structure in the input space. The output space too is the space of bounded linear operators between two norm spaces. So we have the operator norm. So this too is a norm space. In particular, it's a metric space. So I have f prime, a function between two metric spaces. And like we discussed the past 3 weeks, the moment I have a function between two metric spaces, I can ask if it's continuous. And that in this case, I do demand that it is continuous. Any questions so far? OK. And then I'm going to denote by c to the 1, c1 of mn as a space of all, or set of all c1 functions from m to n. But of course, at this point, you should be somewhat familiar with the idea that the moment you see something like this, there should be at least a distance on this, right? So in a previous problem set, we looked at C2, C3, and stuff like that in lower dimensions, and we had different norms and stuff. In this case, we don't quite have a norm here, because n is not necessarily f itself. But still, we can talk about the distance. That is going to be called the C1 distance. This is the natural distance on this set. We would like to make it, turn it into a metric space. OK, so I would like to think of the distance between these two functions, f and g, between the same sets. And I want this distance to somehow incorporate not only the 0th order information, that is to say, how much does f of x goes to some point here, and g of x differ in terms of positions, but also in terms of their velocities as well, or the first derivatives, let's say, as well. And so the way you do this is like this. Define d sub c1 of fg. Well, just like we did in single variable, I need to look at the c0 norm of f and g, so the c0 distance between f and g, and somehow the c0 distance between f prime and g prime. And so how do you do this? Well, first part, and then sup x m f prime x minus g prime x. In fact, let me write it like this. So initially, like we were discussing before, the fact that M is a subset in E and N is a subset in F, these two things are sort of incidental. So that's why I want to think of F itself as a function between metric spaces to begin with. Metric spaces that have additional structure. That's sort of how I'm trying to imagine. Of course, what I wrote before is the same thing as this. But this is a better way of thinking about it. And this, of course, f prime of x is a vector in this vector space. G prime of x, 2 is a vector in this vector space. And if you want to be more specific, this really means operator norm. OK? That's how we define the C1 distance between two functions. OK. And so I guess I should leave it to you as an exercise that if you just consider functions f like this that are bounded with bounded derivatives, then this does become a function. This does become a metric. So exercise. Metric on C1 functions that are bounded with bounded derivative. Now, in this last problem set that we're still grading, there was this statement about, well, the limit of an expression of this form, b sub n, v sub n. And the statement was, if v sub n is a sequence of vectors that converges to 0, and if this is a bounded sequence of bounded operators, so there was this double boundedness, then this goes to 0. That was the statement. Now here too, there's a similar thing going on. So f prime of x, the way we defined it, has to be by definition a bounded operator. But this doesn't say anything about whether or not f prime of x stays bounded as you vary x itself. So I need boundedness of f prime, of this function, that takes a point, associates to that point an operator. I want that bounded also. Okay, that's what this bounded means. Okay, and a final definition here. A C1 diffeomorphism is a function that is C1, that is a functional inverse, F inverse, and the inverse is itself too is C1. C1 diffeomorphism from M to N is a C1 function that has a functional inverse F inverse, so f to the minus 1, that has a functional inverse f to the minus 1 that goes from n to m, so it goes backwards. That is also C1. C1 diffeomorphisms ultimately are going to be the sort of more higher level analogs of what you would call U substitution when you're doing an integral, when you're trying to compute an integral. So instead of saying a U substitution, we're going to call it a diffeomorphism. Diffeomorphism, of course, is somewhat perhaps more sophisticated of an idea. Now, as you can imagine, this is yet another one of those isms, right? So we had vector spaces, linear isomorphisms. Then we had metric spaces or topological spaces. We talked about homeomorphisms, okay? So these homeomorphism is, for instance, a function that preserves the topological structure. Then we had bi-uniform homeomorphism, bi-Lipschitz homeomorphism. These are all equivalences in different senses. Diffeomorphism is equivalence in the sense of calculus. Okay? And as an exercise, or maybe as an addendum to the finite dimensional or fundamental theorem of finite dimensional norm spaces, I can say that a linear transformation from Rd to any finite dimensional norm space of d dimension is an isomorphism if and only if it's a diffeomorphism. Finite, so fundamental theorem of finite dimensional norm spaces let W be a d-dimensional norm space and let's let A to be a linear transformation from Rd to W. And A is a linear isomorphism if and only if it's a C1 diffeomorphism. Okay, I'm not going to prove this. It follows from one of the exercises I left, namely that a linear transformation is bounded if and only if it's differentiable, in which case its derivative is itself. That was an exercise I gave you last time, I think. That's a very nice exercise. And so what does this mean in simple English? It means that when it comes to finite dimensional norm spaces, up to first order, doing calculus on these finite dimensional norm spaces is the same thing as doing calculus on Rd. Okay, up to first order. So we're going to look at later C2 diffeomorphisms, C3 diffeomorphisms, and so on. So that's about being able to discuss higher order ideas. Another thing too is that here you should be somewhat confused about things, perhaps. Namely that the whole sort of structure of this class so far was this. I defined a certain mathematical object using certain axioms, and immediately I defined what it means for a function to preserve those structures. So we defined, I mean, I just said that there's vector spaces, and then we immediately looked into linear transformations. We defined vector spaces, and then we looked at immediately continuous functions, and so on. So somehow, there is in this picture missing the axiomatic definition of what it means for something, for an object, to admit calculus somehow. What does it mean that I can do calculus on M and whatever? That is sort of what I was referring to or alluding to a little bit when I was talking about how there's this distinction between special relativity and general relativity in physics. And similarly in math too, there's local objects and global objects. The fact that I can, so the moment I take M and N, open subsets in norm spaces, I am basically bypassing the need to define these objects on which you can do calculus. But ultimately, the notion of a manifold is that. Manifold is mathematical object on which you can do calculus. It's as simple as that. Defining it as more precise is it takes a little bit more time, and we don't need it in this class, so we're not going to do it. But eventually, if you keep taking more and more advanced classes, you'll see some definitions. What we will do, though, we're going to define eventually something called a submanifold. Okay? We're not going to define what a manifold is, but we're going to define what a submanifold is, surprisingly. Okay? Because ultimately, when you think about it, certainly you should be able to do calculus on a circle. Imagine a function defined only on the circle, taking real values. Now, this is not an open subset. It's a subset of a norm space, but it's not open, you see. If I were to take any point here and just perturb it in this direction, I'm leaving the set. So far, we don't know how to do calculus on the circle, for instance. OK. Any questions about any of this? Now, inverse function theorem 2, a theorem that we're going to spend plenty of time on, is going to be about establishing this diffeomorphism property. We would like to be able to say something along the lines of the following. We would like to say, if I have a function that is C1, continuously differentiable, and it has no critical points, so its derivative is never 0. Derivative is an operator. OK, it's not the 0 operator. Then I would like to be able to say that this function actually has a C1 inverse. It's a C1 diffeomorphism. Okay? Similar to how you would do this in 1 dimensions. Right? You would say, let me draw this diagonal. If this is my function, well, let's say here, the derivative is not 0, and I get to invert this function, you say. But of course, much like in the one-dimensional setting, this inverse is not going to be a global diffeomorphism. It's not going to be a diffeomorphism as such, but we're going to call it a local diffeomorphism. It's going to be a function that is defined on an open subset. It's a much smaller open subset in principle. Okay, we'll get there later. OK, so let's look at the following. Let's fix a point x and a vector v. You see, even though M is a subset in E, and technically points in M are also vectors, it's better to distinguish points and vectors even at this stage. So example, or maybe definition. Example. OK? I have a point x in M, a vector in E. Now, it doesn't matter from the mathematical point of view what you call these, of course. You can call this a potato, and you can call this a blackboard if you want. But it doesn't matter. But this is sort of, I hope, let me put it this way. This interpretation helps me sort of guide the formalism. Consider, well, gamma. And if I want to be more explicit, it's going to depend on x and me. It's going to be a function from reals to E. At time t, OK, this is going to be x plus tv. OK. T is a scalar. I can take this vector, scale it by t, and add it to this point. Certainly, this is just the line passing through x with velocity, right, v. OK? So let's try to figure things out. Even if my input space is one-dimensional, the definition of differentiability should still apply here, okay? So I'm going to look at this, and I'm going to try to write it as gamma of t plus the derivative times h plus higher order terms. So what is this? This is, okay, so depending on our context, h is supposed to be a scalar also. And then I get to split this, like so, plus hv. OK, so this is nothing but gamma of t. And this I can think of as v times h. OK? And so v here, then, is nothing but gamma prime of t. The derivative of gamma at t is this. For any time. Are we happy about this? Yes.
Why are we allowed to just add the 2 points from different spaces?
Yes, I mean, of course, m is in E, so I have these straight lines available in this situation.
M is in E?
Yeah. M is always in E.
Oh, okay.
It's a standing assumption.
Oh, right, okay.
Yes.
Then not.
Yes. But you're right. In general, this is the suspicious part. From a sort of perhaps type point of view, this is a point type object, or position type object. This is a velocity type object. But because we're assuming that m is a subset in this vector space, you get to do this. In general, when you try to switch over to global calculus, you have to do something else, OK? But for us, it is available. Are we happy about this? No, but there's a problem. Because technically, the way we defined it, this derivative, when it exists, it has to be a linear transformation. Right? If gamma goes from here to there, gamma prime of t should be a linear transformation from here to there. But how is it the case that a vector in E is a linear transformation from R to E? Seems it doesn't add up. So that's a riddle. Okay. Of course, there's a couple of identifications happening here. The point is that any vector in any vector space can be thought of as a linear transformation from reals to E, to the vector space itself. Now, for instance, imagine this. Okay. So let me write it like this. Right. This is a space of tuples, 2, 1. Okay, that's a vector. But if you were to think of it as a matrix, you would write it as a column matrix, right? 2 by 1. Under this identification, whatever. But any m by n matrix is supposed to be a linear transformation from Rn to Rm. In which case, this 2 by 1 matrix should be a linear transformation from R1 to R2. So you get to take this, use it to left multiply any 1 by 1 matrix. That's a number. Okay, 2, 1, 1. And the result is going to be 2c, 1c, of course. So matrix algebra itself allows you to imagine vectors in a vector space as linear transformations from R1 to the vector space itself. This is confusing, and often people don't mention this. But somehow linear algebra is ambiguous this way. So, and we've been using this terminology in this class for so long now, but it does start from linear algebra, this ambiguity. What is a vector? It depends, right? A matrix is a vector, perhaps, or a vector is a matrix, perhaps. What's an operator? It's a vector. It's a matrix. They're all the same, and they're all different somehow. So it all depends on how you're interpreting things. Okay? But ultimately, no matter how you interpret them, insofar as your interpretations are consistent, things should be fine. Okay? The same ambiguity you have, oh, is this a vector? Is it an operator? Right? The same ambiguity gets amped up in calculus. Okay. So that's a function, and it is differentiable. Its derivative is this. So gamma is a function, and gamma prime always exists, and it's a constant function. Right? For any t, gamma prime of t is v. It's a constant function in t. Well, constant functions are continuous. Therefore, gamma prime is continuous, which means that gamma is C1. So you would say that gamma is a C1 path, continuous differentiable path, in the normed space E. And of course, when you think about it, it should be the line, right, passing through the point x in the direction of v. And this m is something like a blob around x, which means that the graph, or rather the trail of gamma, should skewer m. Do we see this? OK. Now we can define directional derivatives. Definition. Let f be an arbitrary function. I'm not assuming that it is differentiable at any point. Okay, I'm just going to define something. I'm going to take an x in M and v in E. Then the directional derivative of f at x in the direction of v is in the direction of v is, let's write it like this, d sub v of x, sorry, d sub v f of x, which is this limit. T goes to 0. Oh, I can write it like this. Much easier. F composed with this path differentiated and then evaluated at 0, if it exists. So if it exists, it has to be a vector in the output vector space, provided the derivative exists. Let's draw a picture. So f is a function from m to n. So that's E. That's F. I have here one blob that is called M. And here is another blob called N. I have here a point X. And my function f goes from m to n. Takes x to some point, f of x. Now what is happening? What is this directional derivative? What I do is the following. I take a copy of the reals, and I have this specific path, gamma, that is the that corresponds to this straight line passing through x in the direction of v, right? So I have here, let's say, this v. And now, and somewhere here is 0. Gamma is a path, it's a C1 path in E. Right? So assuming that this is, let's say, positive infinity, as you're going from here to there in terms of the times, here you're moving from here to there. And in particular, at time 0, you're exactly at 0, at x. Okay? No, but then what I do is the following. I take this line in E, and apply f to it. So I'm looking at this composition, okay? The function composition goes from here to there. And in particular, for instance, at 0, this part is going to take it to x, and f is going to take it to f of x. So somehow, output is going to be, again, something that passes through this. Okay? I don't know at this point if this is, in fact, a differentiable path, because I don't know anything about f. Okay? I don't know even if this is continuous, actually. Provided the derivative exists. I'm defining it this way. But what I do is, well, I just look at this limit and differentiate. So let's try to figure out what this means. Does this picture make sense so far? Okay. So ultimately, somehow, this directional derivative should be related to this. Okay. Let me finish this picture. Let's say that this derivative exists, so that this path too is differentiable, at least at this point. But somehow, it might be the case, typically, so that, as you might imagine, that this vector is not the same vector as this. To begin with, they live in different spaces. So what is the distortion that allows me to transform this vector to this vector? That's sort of what I'm imagining, in a sense. Okay. So I should write it. So this vector then is dvf(x). So opening up this definition, okay. What is this more explicitly? Okay. We can do this multiple ways, but let's just use the very definition of the derivative. Right, so I'm imagining this function. Okay. So this should be something that allows me to write the following. I'm going to take the derivative at 0. Okay. I just looked back at the definition of the derivative of a function, and I applied it to this function, this composition, at this point. Whatever this expression is, it should be something that fits into this, okay? Assuming it exists, of course. And here, h is a number. It's a scalar. Okay? And so I can organize this a little bit. In the numerator, I have the norm of a vector. And I have in the denominator too, I have the norm of a vector. But this is a special case because the vector in this case is one-dimensional. Any scalar is a vector too. But once you have one dimensions, it's a scalar anymore. No. And so what I can do is I can again distribute this denominator into this numerator. And I can write it like so. And I can open this up as well because I know the expression of this. F of x plus hv, this is this term, minus this term, minus f of x, right? Because if I plug in into gamma 0, I know that I'm going to be at x. So this is this, divided by h, minus this vector. But you see now this h cancels out because h is a scalar. When I divide it by its scalar 2, it's going to go away. So that's that. It's an f. You see, as opposed to the big derivative, the regular derivative that we were discussing, when you're trying to compute directional derivatives, you get to say, oh, the directional derivative is the limit of the thing that you're familiar with from 3210. So So when it comes to directional derivatives, as opposed to the derivative as such that we defined, you get to compute using the standard rise over run. And of course, let's look at the type of this as well. Even though I'm writing this as a ratio, you should think of it like this. F takes values in n, in particular in f. This too is in f. So the numerator is a vector in f. The denominator is a number. So this is a scalar multiple of some vector in f, which means that insofar as that limit exists, it has to be a vector in f. OK? Questions? Comments?
Will you explain one more time in the picture you drew, just the yellow chalk?
OK, let's do it like this. So I have a function f from m to n, OK? And now I took this straight line passing through the input point x in the direction of v. Now I look at the composition. This again depends on only a scalar. OK? So I think it's safe to think or imagine it as a path in the output space. It actually doesn't escape n. Okay? Something in n. Maybe it's that much. Okay? I just applied the function composition. But then, just like v, where the derivative, or rather the velocity of this path at this point, I can ask, what is the velocity of this image path at f of x at the corresponding point? That is the directional derivative. Does this make sense? OK. Any other questions? So it's easier to compute, but not as well behaved as the regular derivative. Okay. But here's one observation. If f were differentiable at x, then certainly I could apply the chain rule to this. If I didn't assume that f is differentiable at x, I couldn't split this as the derivative of this times the derivative of this. But assuming that f is differentiable, then I get to apply chain rule. OK? Observation. Assume f is differentiable. At x. Then, by the chain rule, for any v in E, what is the directional derivative of f at x in the direction of v? By definition, it's the derivative of this composition at 0. That's how we defined directional derivative. Okay. Applying the chain rule tells me this. This is the same thing as f prime at gamma of 0 times gamma prime at 0. What is this point? This path at time 0 is at point x. So this is nothing but x. And what is the velocity? It's v. So this is nothing but f prime of x applied to v. This is very bizarre. Okay. Assuming this exists, this directional derivative becomes equal to this. But it might be the case that without this existing, this still exists. Okay? That's why I defined this instead of this first. And I'm going to give an example in a second. Another thing, too, is that you should start working actively on this idea that whenever you have a formula, any part of that formula acts on any other part of the formula. Okay? And so here, if you think of it like this, oh, I have f prime of x. That's an operator acting on v. But from a different perspective, it is v acting on f. Okay. In, I think, week 1, we saw a similar example to this. We said, right, so we had this exercise. Reals is the same thing as the space of linear functions from reals to itself. And how did we do that? We came up with, we said, oh, if I have a function L, I can send it to where it takes the input value 1. So somehow, initially this was an operator, and it was acting on the number 1. But then I flipped the perspective and thought of the number 1 acting on the operator. A similar thing is happening here. Okay? So everything acts on everything else. Okay, so here's an example. Oh, okay, this took longer. But the example I want to give is this. I want to do more explicit calculations. At least let me just mention what the example is. Preview. That's a function from R2 to R. At 0, it turns out that all directional derivatives exist. But this function is not differentiable at 0. Very paradoxical. And that's why I initially defined what it means for a function to be differentiable. Okay? Directional derivatives, it's a slightly different thing. Related, but different. Okay, that's a good place to stop. Thank you. I'll see you on Monday.